could pick a random number. Let's do Java has a random class, right? And if you say r.next double, double d equals r.next double, what is this number? What kind of number do you get out of it? Yeah, this is a uniform distribution by which we mean uniformly distributed between the values of 0 and 1. Every programming language has some way to get a random number in that range. A lot of people are familiar with, in C, they call the rand function, which returns an integer from 0 to rand max. So what they'll do is they'll say double d is equal to, cast that to a double, divided by rand max. And now this is a double precision floating point number, uniformly distributed in the range from 0 to 1, right? And it happens to be formally the range 0 inclusive to 1 exclusive, meaning it might be 0.999999999, but it will never be 1. And presumably all of the values, including 0 and not including 1, are considered candidates and are equally valid for being numbers in that range. Right? Okay. First of all, never use that one. I think I said why, because basically it's slower than mine, and division's actually a pretty slow operation, and it doesn't have as nice random properties, and it turns out rand max isn't as large as you'd like it to be. To actually get all of the values in your mantissa, meaning the part of your double that matters for random numbers, to be random, this doesn't fill them all up. It's only some number of those digits are actually random, and basically just don't use the C version. If you use my my rand.uniform function, then you're getting a good random uniform value. Okay, supposing you do that, and you have a whole vector that you want to initialize. For right now, let's just call this vector W. But suppose W is some range of values. I picked W to imply weights. Suppose every single element in it is going to be filled up with random values uniformly distributed from 0 to 1. Is that a good way to initialize your weights? Now, the answer you're thinking right now is, well, that's not the way you told us to initialize your weights, so probably the answer is no, and what great deductive skills you have. But that doesn't help you answer the question, why? What's wrong with this way to initialize your weights?
There's no way to initialize it.
What's that?
Know something about it. Because you don't know what the optimal solution is.
That's true.
So you just pick initialize randomly because there's no way to determine if it is good or not.
Yeah, good way to put it. So we know the weights are going in a neural net, right? And what else do we know? That's about it. I mean, yeah, we're going to train it on handwritten digits, and if that was meaningful, I'm sure that could run through your brain and produce something meaningful here, right? Except that's sufficiently convoluted that basically we kind of want to say we don't know anything. Is this an unbiased way to fill in the weights? Well, first of all, it's biased to be positive because there's no negative values there, right? So suppose instead we adjust it so we're going to pick random values from -1 to 1. How do you draw random values from -1 to 1? You draw from a uniform distribution, you multiply by 2, then you subtract 1. There you go. That wasn't hard, right? You guys are awake today, right? Because I'm recovering from the flu, so, you know, I'm not the one that doesn't have an excuse to not be dead today. That was a lot of negatives. and my brain didn't fully parse that either. Okay, well, just kind of grunt every once in a while when I talk. It makes me feel comfortable. Okay, here's what I'm getting at. Let's pretend there were only 3 values in our weights, just because that would make it easier to plot. Darn it, that's 4, isn't it? Okay, now there's room for 3 numbers inside of this vector. If we had 3 numbers uniformly distributed between -1 and 1, and then we were to plot those numbers, they would kind of fall in a unit cube, right? And by unit, I mean, well, this corner is, if this corner is -1, -1, -1, and this corner is 1, 1, 1, and the origin of the universe is right there, then the random values that we drew would all fit inside the box. None would be outside of the box, and they'd fill up the box, and everywhere inside of the box would have, every little region in the box would have about the same number of random points inside of it, assuming it's a good random number generator, right? Okay. Is this an unbiased vector? I think it's clear the answer is no, because if it were unbiased, then if we started at the origin and we pointed to any of the points, pick one of those random points inside of the box, and we call it a vector. Do you agree with me that vector is not pointing in an arbitrary direction, it's pointing in a biased direction, right? Whereas if we achieved what we wanted, would it not look more like this? That's not a circle, it's a sphere. To prove it, I'll draw the reflection of a mysterious window that happens to be somewhere. Now it's clearly a sphere, right? Okay. So now we have this 3-dimensional sphere, and now if we picked a random point inside of the sphere and we drew a vector from the origin to some random point inside of that sphere, then this would be unbiased, and I claim that's biased. Do you agree? Because any point inside of the unit cube, there's more of them in the corners than there are on the sides. That's not true, there's the same amount, but there's more vectors pointing towards the corners than there are vectors pointing towards the sides if we visited all of the points in proportion to their distribution. So I'm going to say this is bad, this is good. How do you do it in code? Yeah, as it happens, if you fill your random vector W with values drawn from a Gaussian distribution, this is just one of the mysterious and wonderful properties of the Gaussian distribution, or the normal distribution. You know, the Gaussian distribution is another name for the normal distribution. Okay, Gauss invented it, and it's so common that it's now called the normal distribution. Okay, well, if you fill it with values from a normal distribution, that is completely unbiased and will point in any direction. Turns out they don't fill a unit sphere like this, they actually fill a unit Gaussian, which means there's some probability that they'll be off to infinity. But if you can imagine a Gaussian spun uniformly over all possible directions, so that basically all directions are equal likely, but the magnitude is going to, within the probability of 1 standard deviation, be within this region, and 2 be within 2 deviations, and so forth. That was not even English. Just look and comprehend and get it.
So you're not guaranteed to be in the circle, you're just really likely to be?
Yeah, that's what I'm trying to say. Thank you. Words gone.
Why do you think cubes is bad one?
What's that?
You said there'll be more vectors
Yes.
Why?
Good question.
Isn't any given point in the cube equally probable?
Yep. Because every given point in the cube is equally probable, precisely because of it, there's more vectors that point to the corners. So let's just do a really lame
Vector
empirical study.
have the same magnitude? It couldn't. Are we talking about every point within or just on the boundary?
I'm saying every point within. It's just, it would take a darn long time for me to draw them that way. So, yeah, pretend I've divided it all up, right? Let's see. Now we just start counting. That didn't work because I drew it on the edge, but the origin's way over here. Let's see. Here's a better way to illustrate it. Suppose we have a point, and we draw bink, bink, and now I'm going to copy these and paste them on top of each other. This won't take very long, I promise. Because of exponential growth. Okay. I think you'll agree with me that these points are uniformly distributed, right? And yet, if we start drawing vectors from the origin, around here, those vectors are nicely separated, right? See how they're kind of crowded over there? I might have subconsciously exacerbated the problem slightly with my mouse, I don't know. But nevertheless, there's lots of room to wedge your hand in right there if you wanted to wedge your hand in right there, but right here it gets a little tight, right? And you could imagine then that if this were, instead of just one wall, that it were a square, basically there's more vectors pointing at the corners than there are at the sides. Now that's just along the side. How about if I put it this way? Certainly you agree that all the points uniformly distributed within the sphere are not pointing to any corners because there aren't any corners, right? Well, now if we take this sphere and we embed it within the cube, what's left over? Just the corners.
Oh, and the cube is just the corners.
So if you now also add some points on the corners, now we want to say, isn't that a little unfair that you added some bulk in, you know, these 4 parts of the sphere? Of course, there's going to be 8 parts because it's a cube, not a square. But basically, it just doesn't feel unbiased anymore. It's an intuitive level proof. It's not a formal proof. But are you sold that squares are biased and spheres are unbiased? Yes?
What exactly do you mean by bias? Do you mean like the numbers that are chosen for each coordinate are dependent on one another?
Yeah, what I mean is there is some arbitrary decision going into it. There's something besides. Okay, I guess I'm asking you to first take for granted that pointing in an arbitrary direction is the stated goal. And if pointing in an arbitrary direction, if you accept that as the definition of unbiased, then I think it's pretty clear that, maybe I should stop using the term. It should be clear that drawing randomly from a square leans your vectors towards some general thrust, whereas vectors randomly drawn from a sphere, it really says nothing. If you knew something about one element, you would know nothing about the next element. Whereas if you had drawn from the square, you could. You could look at one element and say, oh, where is that? Well, then probabilistically speaking, because it's around here, I must have one of those values in order to get myself closer to a corner where it's more likely to be.
Well,
Yeah.
in the sphere, can you say that like if the magnitude of the vector is higher, meaning one of the coordinates is really big, then all the other coordinates must be smaller? Or would that be? 'Cause, like the further you go away from the center, then any perpendicular dimension must have a shorter radius for the point to like fall in the sphere, right?
Yeah, well, technically it is a Gaussian. I'm going to claim, though, that it holds with both Gaussians and spheres. So if we had drawn random values from any point inside of the sphere, and so in fact, if you want to draw a random point on the shell of a sphere, the way to do it is you fill a vector with random values from a normal distribution, and then you normalize the vector so it has a length of 1. If you do that, you're clearly on the shell. If you want to draw within a sphere, then you do that, and then you pick a random point on the distance from the radius to the surface, and then you multiply by, or divide by the radius, or something like that. Can't remember what you do. You do something to compensate for the fact that you want to have equal density all along, and then you have a random point in unit sphere. So either one can be done. Suppose you do it. I don't know. This is where my train of reasoning just dies. I'm just going to come out and say it authoritatively. Basically, you want to point in an arbitrary direction, circles do that, squares don't. Deal with it. How about that? Okay, sorry. That's not a great answer, but I'm just not working today. Yeah?
So, I mean, I get that. I don't really get why it matters that our weight vector is a bunch of random unbiased numbers. If there was anything, couldn't it just put more around it?
It can, in theory. There are some reasons it can't, and yes, that's what I'm building up to. So